dudes, Dude the Builder here, and in this episode of Zig and Death, we're going to be talking about memory management, starting our exploration of this aspect of working with Zig. And this is a really important topic when we're dealing with any low-level programming language, but even more so in Zig, because Zig puts extra importance in giving the programmer total control when it comes to memory management. In that respect, Zig is even a lower level language than languages like C, C++, or Rust, because those languages provide certain aspects of memory management which they handle automatically. For example, having a default memory allocator. And in Zig, there is no default memory allocator. When you're going to do any type of allocation on the heap, you need to specify which allocator you want to use. And that gives you total control about what allocation strategy is going to be used and how to handle error situations like out of memory. Okay. So, as a foundation for this type of management topic, we have to cover or refresh, if you already know these concepts, the basic sections of memory when we're dealing in this type of systems programming. And basically we're going to have what's known as the stack, what's known as the heap, and what's known as the static or global constant, global data area. This area that I have labeled as static in memory is basically the area where the information from your compiled program is going to reside. When you compile the program into a binary executable file and then you run the program, well, that information in the binary file has to be loaded by the loader into memory, and within that area where that data from the binary is loaded, you can have certain values, variables, constants. We're going to be seeing that in the code, which types of variables would be located in this static or global area. But aside from that, once that area is loaded into memory and the program is executing, you're going to be mostly working with the stack and the heap. Okay. The stack is where anytime you are calling a function, there's an area that's going to be separated for that function in the stack, and that area is normally called a stack frame. That stack frame, the size of that stack frame may vary from operating system to operating system, and in some cases may even be configurable. You could be talking about kilobytes to megabytes. But the important thing here is that when you call a function and that function is going to do whatever it's going to do, it's going to be executing and using the memory in the stack within that stack frame that has been created for it. And once the function returns or finishes, that stack frame is removed from the stack and that memory is no longer available. Okay, so that's really one of the most important aspects of memory management, and specifically like in Zig, when you're doing manual memory management, you have to be really aware that whatever is within the confines of the stack frame is going to be destroyed once the stack frame is eliminated, and that happens when the function returns. Okay. Now, on the other hand, the heap is an area of memory where you can allocate space, and that space will basically live for as long as the program is executing, unless you free that space using logic inside your program. Okay, so if you have some type of data that has to outlive a function, then you would put that data on the heap. Okay. And that's what we're going to be taking a look at. That's basically what's known as allocation when we're talking about manual memory management. And even in dynamic memory management, languages that do have garbage collectors or that employ other techniques for dynamic memory management, they are also behind the scenes allocating on the heap. Okay, so let's go to the terminal. And here I have a file called sections.zig, which basically demonstrates in Zig code the mapping to these different areas of memory. And why is this important? Well, when you read in the Zig language reference, there's a section about memory, and more specifically, there's the question of where are the bytes. Okay, that's basically the question that you have to be asking yourself whenever you're dealing with manual memory management. Because depending on where the bytes are located, that's how long they are available. That's when you can determine if a certain area of memory is valid or invalid. Okay. Here we're going to see examples. When you have a constant and that constant is assigned a value that's known at compile time, this constant will live in that global constant section, the one labeled static that we saw in the diagram. Basically, within that area of the actual data from the binary that's compiled. And here we have an example of a string literal, which is the same. It happens the same thing. Remember that string literals are pointers to sentinel terminated arrays. Well, that array is going to be located in that global constant area, okay? And the pointer will be pointing to that area. When we have variables that are at the file level or at the container level within a struct or something like some other container type, then that variable will also be within that area designated for your executable program. But in this case, it's an area that can be modified. It's the global data section. It isn't just read-only. It can be written to. But here kicks in the really important part of a statically typed language, since we have to specify the size via the type. Okay, so we know the size of this value because the type is a usize. Okay, so when we compile, we can set aside that number of bytes in that area of memory for this variable. Okay, so here we're going to see an example. We have this little function called locals, and it returns a U8. And in here we see examples of local variables. Okay, we have a, b, and result here, and we are returning result. The important thing to note here in terms of memory management is, like I mentioned at the beginning, these are local variables within the context or within the confines of the function's stack frame. Okay, that means that when the function returns, that stack frame will be destroyed, and all these variables, all that area in memory is no longer going to be valid. Okay, here we don't have any problem because we're dealing basically with what's called usually called primitive types. In this case, numeric types, U8. And primitive types are types that can be easily and cheaply copied, and they don't need any resource management, like, for example, memory being allocated or deallocated. And when you have that type of primitive value, you can return it from a function without any problem, because basically what's going to happen, it's going to be copied and return that copy to the caller. Okay, so even if result is within the confines of this stack frame, which you could say is this part of your program, that copy will be returned from the function, and there will be no problem. Okay, now we have a function here that says bad idea. This one returns a pointer to a U8. Okay, and here we're defining a variable x, and we're returning a pointer to x. Okay, with the address of operator. And the thing is that x, as you know, lives within the stack frame of this function. So when we return from this function, x will no longer be valid, and this pointer to x will no longer be valid because it's pointing to an area of memory which is no longer valid. Okay, so if we have a situation where we want to return a pointer, you have a function that returns a pointer, that has to raise like an alarm bell in your head, because that pointer cannot be a reference to local variables that live on the stack, specifically the stack frame of the function. Okay. Here we have another function that's called bad idea 2, and we demonstrate the same problem with a slice. Okay, we have an array here of the characters HELO, and here S is a slice that we're taking from array from index 2 onwards, and then we're returning S, okay, because that's what we're saying here, that we're going to return from this function. And as this comment says right here, remember, pointers or slices are also pointers. Okay, that's why they call them fat pointers, because it's a combination of a pointer and a length. And let's go over to another diagram. Here we have a diagram that's basically showing the problem with what we're doing in that function. We have the stack. As you can see, the heap is right here, and it's totally empty. The stack here contains our array, and we created that slice, which is the pointer, which is pointing here to the second index in that array, and the length. Okay, and the problem is, as you can see, everything here is living on the stack. So once this function returns, all this memory is going to be freed. It's going to be destroyed basically automatically. And if you copy this slice and move it out of the function, like we're doing by returning it, let's go back to the code. As you can see here, the slice itself is basically a pointer, which is kind of like a U size in terms of size. It's an address basically. And it's the length, which is another U size. So in terms of being able to be copied easily, like a primitive type, you can copy a slice easily, just like it's like a primitive type that you can copy. But the problem is that the pointer is still pointing to memory that's within the stack frame. Here in this case, we're pointing to this array. Okay, so once this function exits, we can have a copy of the slice, but that slice, the pointer specifically, is going to be pointing to memory that's no longer valid. Okay, now here comes the part where we start seeing how we solve these kinds of problems in Zig. Okay, we have this version that's called a good idea, and when we are going to allocate memory on the heap, which would be the solution in this type of situation, we in Zig, what we do is that a function that's going to allocate will then receive as its first parameter an allocator, which is of type std_mem allocator. Okay, and std_mem allocator is basically an interface. Any type of allocator can match up with this interface type. And the function then, since allocation can fail, I'm explicitly listing out here the type of error, which is a std_mem allocator error. But you could just either add this error via merging it with an error set of your own, or leave it to be inferred, okay, by just specifying the function return type, the return union, like this. But I'm listing it out explicitly here just for information purposes, so you know which type of error could be returned in case of allocation. And in case of success, it's a slice of U8. Okay. So let's see how this is done. We create the array once more, but now what we're going to do S is going to be a slice, but that slice is going to be returned from the alloc method of allocator, of the allocator that was passed in. And alloc takes two parameters, the type of what we're going to allocate and how many. So we are specifying here that we need 5 U8s, which is basically the 5 items we have in this array. And then we use this handy copy function that we have in stud mem. We give it the type once more, the destination, and the source, which is destination and the source are slices, the S that we received from alloc, and a reference to our array, which will coerce to a slice. Okay, and now we return S. And with this version, we don't have any type of problem, because S is now a slice that whose pointer is pointing to bytes allocated on the heap. Okay, and the heap will outlive the function frame of this specific function. Okay, now it's important that when you have this type of function, you add some type of dot comment. Let's say like this. This is caller must free returned bytes. Okay. With this type of comment, you are making it clear to the caller of this function that they're passing in an allocator. We are allocating, we're returning a slice, so those bytes that the slice is pointing to, you have to free them later on. And we're going to see further down in this video how to do that. But for now, this would be the way of how to solve this problem that we had with our functions that were trying to return memory that was located on the stack. Okay, you allocate on the heap, and then you can return that. Okay, now let's go to our main file, and we're going to see a couple of options that traditionally you can find in low-level programming languages like C. And in Zig, you can also make use of these idioms. The first one that we're going to look at is this function called cat outvar len. And basically, this is a strategy where the function itself is not going to allocate. Okay, you're asking the caller to allocate memory and to pass you a variable, which is conventionally called the output variable or an outvar. And whatever you're going to be writing in that function, you write it to that allocated memory that you're being passed in this case a slice of U8. Okay, and we're going to return a U size, which is going to be how much how many bytes we wrote, okay, in that output memory that we're being passed in. So in this case, what we do, once again we use we're going to be asserting first that the length of that slice that we're being passed in as the output var is greater than or equal to the concatenation, to adding the length of the two strings that we're being passed in to concatenate. If so, here we use the stubmem copy to copy the first string, starting from the beginning of the output slice. Then, starting from the index of the length of the first string, we copy the second one, okay? And then we return the length of the total concatenation, which would be the addition of both of these lengths. Okay, now how would you use this type of function? Well, we have two strings here which we want to concatenate, and we create a buffer here, in this case a 128 byte U8 array. We're leaving it undefined, and we call the function here. We pass in our two strings and a slice, which we're just taking the address of the buffer, and that will coerce to a slice as the output var. And we're saving the written bytes to length here, len, excuse me. And here we have an expect equal strings. This operator here, the plus plus, is how you concatenate strings when they are known at compile time. And basically it's an operator on arrays. Okay, so this is an operator to concatenate arrays, but since string literals are in fact arrays, you can use it to concatenate string literals like this. And we're testing buff from 0 to the len that we received. Okay, a clever way to do it, avoiding the intermediary len variable, would be to just slice the buff from 0 to whatever that function call returns, which is going to be the length. Okay, you can do it like this also. Okay, so that would be how we make use of a function like this. We create our buffer, which is basically an array here of bytes, and we pass it in as a pointer to that, which would be coerced to a slice. Here we have another version, and this time it's basically the same thing, but instead of returning the length, we return the slice of bytes from that output of our slice. So we are reslicing, okay, with just the bytes that we wrote. So here, once again, we assert that we have enough space, we copy, and then we return the slice of out from 0 to the length of the concatenation. Okay, and how do we use that? Once again, pretty much the same thing. We create the buffer here, we call the function, but now we are receiving the slice directly. So when we call here expect equals strings, we can compare with the slice. We don't have to slice again our buffer. Okay, now we're going to see a version that allocates using an allocator. It's called a cat alloc. As I said, traditionally and conventionally, the first parameter is going to be the allocator. And we have our two strings, and we're going to be returning the error union. This time we let Zig infer the error, and a slice of U8. Okay, so what are we going to do here? First thing we do, we allocate. And this time we're calling it bytes. And we're once again using alloc, telling it it's U8, and the total of the concatenation is the amount of bytes that we need. We do the copy, and we return bytes. Okay, once again, this is the type of function that you would notify via a comment to the caller that they have to free these bytes once they're finished with them. And here we have a test that I currently have commented out. Let's uncomment this, and let's run our tests, see what happens. And as you can see here, we have 5 out of 5 tests are passing. Okay, all of the tests are passing, but still we have like this error output. And what's happening is that we have one memory leak. Okay, and if we go here to the top of the output, we're going to see it says memory address. It gives you the address that was leaked, and it'll tell you where that memory was allocated. Here when we did our try allocator.lock. Okay, so what happened? Let's go back, let's clear the screen, go back to the code. As I said, we're using here a function that takes in an allocator, so it's allocating. We're being returned a slice that was allocated on the heap, but we're not freeing that memory anywhere. And we're making use here of this special allocator called stud testing allocator, which will check automatically for memory leaks. Okay, this is a special allocator just for testing. We create here like this alias here with this const allocator to make it easier to type out. And that's the allocator that we're using, and that's why we got that output reporting the memory leak. Okay, so what can we do? We have to free that memory, and we can do that with allocator.free and the slice that we received. So that's how you would free the memory. Let's run the tests once again. And as you can see, we have our tests are now all passing, and we don't have any memory leaks. Okay, let's go back here. And one other thing I want to demonstrate, which is really important, is here. Let's look at the code. up here in the function. When we allocate here, and then we're performing basically these operations, we are copying with studment copy, and we are returning. We don't have anything here before returning the slice of bytes that could fail. Okay, so this code is okay just the way it is, but just for demonstration purposes, I have this function here that's called may fail, and it does return an error immediately. So what would happen if, let's say, we are between these copying operations, and we call that function may fail. Okay, so we would have, we allocate, we copy the first slice, we call this, then we hopefully get to copy the other one and then return. So let's run the tests, and now we see that we have 4 out of 5. So we have a failing test, and also we have a leak, a memory leak. Okay, so let's see what happens here. It's telling us that failing test is because, in effect, within a test we are returning the error boom. But also, in terms of the leak, it's showing us here when we allocated the slice. Okay, so let's clear the screen, go back to our code here. So basically, what we have here is a very common situation. You're going to have within a function a place where you allocate, and maybe after, but before returning, you're calling another function that may fail. So what can we do in this type of situation where we're allocating and we want to return what we allocated, but in between the allocation and the return, we can have an error condition that may fail and return an error? Well, in Zig, there are a couple of mechanisms that are available to execute code once we exit scope, and those mechanisms are known as defer and defer. Okay, defer will execute a given code when the scope where you make the defer call is exiting. People coming from Go, for example, may be used to defer, but defer in Go will execute when the function exits. In Zig, it's at the scope level. Okay, so you may have a defer within a block. It will be executed when that block exits. Okay, it doesn't have to be at the function level. And defer is like defer, but it only executes when we're returning because of an error. Okay, so if we have a try like here that produces an error, and that's the cause of the return or the function exiting, then defer is called. Okay, so in this type of situation where you allocate and you want to return the allocation, you don't want to use defer here. Let's complete this. Allocator dot free bytes. Okay, because if you use defer when the function exits, which is the scope that contains the defer, we would be freeing that memory that we want to return. Okay, unconditionally. For this type of situation, we use defer. Okay, now if the function exits successfully, this defer, an allocator free, will never execute. But if there is an error, like here, this defer will execute. Let's save that and run. And now all we have is, as it states here, we have that says 4 out of 5 tests passed, but we no longer have any memory leak. Okay, this is just our error condition, our error boom, but we no longer have the leak. So in effect, the defer is taking care of that situation where we may have an error, and we then, in that case only, we do the free of the allocated bytes. Okay, so let me remove this here. But since I removed what could fail, I no longer need this error defer, so I can remove that too. Okay. And now the last part that I wanted to demonstrate in this initial video on memory management is how you would commonly find structures in Zig that internally make use of allocation. For example, here we have this foo struct. It has an S field, which is a slice of U8. And when you have this type of struct that will need some type of allocation on the heap, what's conventional is you're going to find that you create them by using an init function. Okay, so we have this function here, init. It will take once again a studman allocator, and in this case we're passing in a string, a slice of const u8, and we are returning here the error union of any type of error inferred and a pointer to foo. Okay, so once you see here we're returning a pointer, so this is that red flag I told you. This means that we are either receiving the output var, which we'll use to point to or slice, or we are receiving an allocator and we'll use that to create this pointer. Okay, and that's what we're going to do here. Here what we're going to do is create here this constant foo pointer. We're using now, instead of alloc, we're using create. Alloc is when you're going to be allocating more of one of a certain type, but if it's just one single item and all you need is a pointer instead of a slice, then you use create. Okay, and we give it the type, okay, which is a foo, so we are receiving here a pointer to foo. Now we are using error defer here. Why? Because we are then gonna use another call here. We're gonna allocate for foo's S field, which is a slice of U8. We're going to allocate space for that, and that can fail. We're using try here, so that's why we're using this error defer here to free that pointer that we created in case that this allocation fails. But here we're using a lock because we're going to be allocating more than 1 byte. It's the U8, and it's specifically the length of that string that they passed in. Okay, and then we use our old friend memcopy to copy from that string that we passed in to that field, that slice that we just created, allocated on the heap, and then we return our foo pointer, okay, which is a pointer allocated on the heap to foo. Now also the counterpart to init would be dinit. Okay, it's idiomatic and conventional to see a dinit function that receives has a self parameter, which is a pointer to the type, a pointer to foo here, and here we have an allocator, which is the allocator that we're going to use to free the memory. Okay, there are also instances where the allocator can be part of the data structure itself as a field. And instead of having to pass the allocator in the init, it'll have a reference to the allocator in the struct itself. But here I wanted to illustrate that you can do it this way. Once again, receiving the allocator. And then here, we first free the field S, okay? And then we destroy. When it's a slice that was allocated, we use free. And when it's a pointer to just a single item, we use destroy. Okay, and we destroy self, which is indeed a pointer to foo. Okay, and here we have a test to demonstrate how do we use that. Once again we're using the testing allocator. We create our pointer by using the init function, and then here we are using defer to free those resources by calling the dinit method in the foo pointer. Passing in the allocator once more. here we use defer because we're not going to be using that memory anymore, those resources. We want to unconditionally free them once we reach the end of this block, okay, of this scope. And then we use the equal strings here to compare our greeting, what's in that greeting variable, to the foo pointer s field, okay. So basically, if we save here and we run our tests, we see that we have all our tests are passing, okay, and there are no memory leaks, okay. If, for example, we were to eliminate that line there, and we run this again, we get a memory leak, okay. So that's basically it for this initial video on memory management. I know that for those coming from languages that are memory managed, like for example Go, Python, JavaScript, there are a lot of very new and different concepts here. But we'll be talking much more about memory management in Zig in future videos. Don't worry about that. So I hope you find this useful. Did the builder here. I'll see you in the next one.